This video will talk through the elimination process whenever you have coefficients that are not additive inverses already. So this video will show you how to create additive inverse coefficients to use the elimination method. So I'll look at a problem like number 2, and when I analyze the problem, it seems like y would be the easiest variable to eliminate. If the y in the second equation had a coefficient of positive 2 on it, then I could easily eliminate y and then solve the system. So let's run through the process of how to make that happen. So the first equation is fine as it is, and I would need to introduce the factor of positive 2 to each term in the second equation. So when I do that, I would multiply each term by positive 2. And what I'm going to do now is just simply recopy the first equation. And it's easy to see that this now becomes my brand new system, and I've got the additive inverses. So now when I do the vertical addition between the two equations, I can simply eliminate y. So I whittle this down to one equation for solving by temporarily eliminating one of the variables, and that's why the process is called elimination. And this is going to be set equal to positive 75. When I divide both sides by 15, I discover that x is 5. And now to find y, you can go back to either original equation and let x become 5. Let x take on the value of 5 in either original equation. And so here I will do the first equation. So 7, let x become 5. And then I end up with negative 2y equaling positive 2. So y is negative 1. And I would like for you to get used to writing the answer as an ordered pair. So always wrap it up so that it's obvious that the answer is the ordered pair x, y, and here it would be 5, negative 1. Let's do one more on the video. And I'm going to move now to problem number 3. And let's do a little bit of analysis here before I get started on it. So in problem number 3, just to show you how to analyze the systems, it looks like the easiest variable to eliminate would be y, because I would just need to simply manipulate the second equation. So I would need to introduce a factor of negative 4 to each term in the second equation. If the y that I've got bracketed in red had a coefficient of negative 8, then I would have additive inverses. So let me do that. Let me apply a factor of negative 4 to all 3 terms in the second equation. And then I'm just simply going to recopy the first equation. And now I'm going to add them together vertically. So here's my vertical addition. Y sums out to 0, and x is equal to negative 7. To find y, I'm just going to go back to the first equation. I'll let x take on the value of negative 7. And then 8y, it's set equal to positive 16. Therefore, y is 2. So the ordered pair solution for this system is negative 7, positive 2. And I just wanted to take a minute and point out one thing with analyzing these systems. I'm not going to do the whole process, but I do want to at least talk through what would be involved with eliminating the x. And it's not wrong to eliminate x, it's just a choice. So looking at the x's, it would be most convenient if I had a positive 6x and a negative 6x. So in order to make that happen, I would need to multiply the first equation by positive 2, and I would have to do it to all 3 terms. And then I would need to multiply the second equation by positive 3. And that's going to be 30 and 24, that's going to be 54. And then it's easy to see now that I'm not going to do the whole process, but in this method, the x's would sum to 0, and then that would allow me to solve for y. And you should get the same answer either way. I just wanted to point that out